wanted to go over a couple characteristics of this mock-up, or proof of concept, involving the eddy currents and polarities flipping. Now what I have here is a pole finder, and this is an axial magnet with a simulated wave inside of the copper sheath. I'll do this with one hand. Okay. But when you spin the cylinder, you not only have an axial field, but you have a varying waveform. So this is just a mass of copper, which I'm going to spin with a motor. Now, normally, when you have an axial magnet like this, my thumb is north and my index finger is south, you approach this and it wants to repel, does not want to touch the copper. You have to be here in order to feel this force yourself. But this magnet does not want to touch this rotating copper. The magnet's not trying to spin out of my hands with torque. It's just repelling. So if I were to be able to remove this assembly here and leave this floating on top, it would just levitate above the copper and not spin. Or if I were to flip it 90 degrees, it would spin and flip, but it would slap the surface with a bunch of friction. So you either get levitation or you get flipping of poles with friction. How do you get the best of both while spinning on its centripetal axis? You have to mess with the magnetic field. And what that does is you get the best of both, levitation and rotation, just from being in the presence of the eddy current.
Just the way John has always described it, that it will orbit and spin.
Center here again, so no fooling. Okay, but let's slow the rotation and see what happens. Now it's touching the surface like a tire on the road. Of course it's spinning because it's touching the surface with friction. But we increase the rotation, the eddy currents take effect, and it can't touch anymore. But instead of just hovering, we also get the rotation. And that is important because you want to have a varying field in order to generate electricity. You have to have relative motion and flipping of the poles. But this other side has magnets, or a magnet ring, inside of this big mass of copper. So you have a general axial magnetic field inside of this mass of copper. So now I have this neodymium magnet, very strong. And as I approach, this wants to touch that copper. But just before I get to the surface of it, it's pushing me away. So it's attracting, repelling. So now I can't really pull it away and I can't really push it in there. So there's this happy medium, an equilibrium, to result in an orbit. But because this is a mock-up, we can't display the spin and the lift effect without imprinting the waveforms onto the materials. And in order to do that, you have to machine them to very specific sizes and densities. And it is a lot of work. And I am doing that by myself right now, by hand, one piece at a time. And we need, let's say, 5,000 pieces to experiment with. Perfect pieces. So I might break half of them, which means I need to make 10,000 of them in order to get the goal of 5,000. So it's a lot of work that we could automate if we had the funding to help pay for engineers and personnel in different areas.